All right, welcome. In this video, we're going to explore the recursion tree technique for analyzing the runtime of recursive code or recursive algorithms. If you are interested in the algorithms that we're going to be analyzing here, please take a look at the last video. In this video, we're going to start with our recurrence relation. And so I'm going to begin with one here, and we're going to apply the what's called the recursion tree technique to try and come up with a good guess at a bound for this recurrence relation. All right, got the recurrence relation stated here again for simplicity, and the technique itself going to rely on an analysis of the actual recursion tree. Now, for this problem, we're going to take a look at this recurrence relation. We're going to notice that there's only one recursive call on each step. Again, if we looked at the recursive code related to this, we would also notice that. So the recursive tree that we actually end up building is not very much of a tree at all. It's more of a branch, just sort of one long stick. So when we're analyzing this, what we want to think is we've got multiple levels. Maybe I'll leave a little space here. And at some level down below, we're going to get to a terminating condition. Maybe I'll draw a little square there instead. Again, there's going to be some kind of internal nodes as well. And we want to analyze, as we go down this tree, each recursive call, how many operations are carried out on each level. So let's start here with something that's a little bit easier. We're going to start here, and I'm actually going to make an executive choice here to label my first level 0, and that's just because I've looked ahead. I know what's going to happen, and the math's going to work out a little bit better if we start labeling our levels at 0. In this column here, I want to keep track of how many there are on each level, and we've already stated that actually there's only one on each level, and this is something that's going to make things a little bit easier for us in our analysis. And this is also an example of what we call decrease and conquer. A decrease and conquer is a very special case of divide and conquer, where we have only one recursive call at each stage, which again simplifies our analysis a little bit. What's the size of each of our nodes here? Well, on the main level, our size is normally n. Usually we only have one variable n. And the cost, how much does the node on this level cost? Well, here we're actually talking about the extra cost. The recursive cost, we're going to worry about that on the next level down. Okay, the next level will take care of that. But on this level, we do carry out d extra operations. Okay, so we have d extra operations on this level. Let's go to the next level down. Again, I've already drawn it. It's only got a single one. I'm going to call this level 1. How many on this level? Still 1. This column obviously is going to be full of 1s. But the size of the next level down is given here, n minus 1. How much effort is carried out on the next level down? Well, each level is only a constant amount of work being carried out, and this is something. This is a pattern that we're trying to identify, and well, because it's the same at each level, this is a fairly easy pattern to identify. But to explore the technique a little bit more, let's go one more level down. Usually we're going to keep doing this until we encounter a pattern. So next level down, okay, we see the pattern here. We can probably guess the pattern here. We're going to be at n minus 2 now. And again, nothing changes. Level to level, we do the same d amount of effort in the worst case. So moving down here to a more general case, I'm going to call this level I. Level I will still only have one call, but verifying here, let's be careful. On level 0 it was n minus 0. I could put that in there if I want. Next level n minus 1, n minus 2. So it looks like the pattern is we'll be at n minus I when we get to this level. And again, this pattern was easy. It's a d, and it's d's all the way down. Okay, so what about this last level here? So again, there's maybe some ... here, but the last level down, And I'm going to call it k for the moment. The only thing about this level that really is of interest to us is that this will be our base case, which is a case where our size is going to be less than or equal to 1. And maybe I'll put that there. Although specifically here we're saying n minus k, because if we're on level k, the size should be n minus k. So we're going to get to a point where our n minus k is less than or equal to 1. And actually, this little calculation is going to become important to us in a second, so I'm going to maybe flag that. How many will we have on this level? Well, still 1. Nothing's changed there. And what's the cost in this level? And we need to be careful. We did identify a pattern here, but this was for all the recursive calls. When we get down to this level, this was our terminating case. We're now on this level. It's actually C on this level. All right. We've actually completed we filled out this table now. And actually, if we want to know what the total cost of the whole tree is, we've got the cost of each level here, or maybe if you want the cost of each node on each level here. So the cost of the whole thing then must be the sum of this column here. And again, we might be able to quite quickly see what this is equal to if we're a little bit more clever, but I want to practice the technique here. So I'm going to notice that we can actually write the sum of this as two terms. The first one is going to be C. This term by itself is usually a term that is by itself. So the bottom level, because it's different than all these recursive levels, is the terminating level. It pops out by itself as a single term. So I'm going to include that one as a single term. And then we now need to investigate, or we now need to express the sum of these other terms. Now again, we can probably see it's d times something, d times something, but I am going to express this here. Later on, we're going to encounter terms that aren't just a constant all the way along. In a different video, we might have a function here that changes over time, and we might end up getting here, instead of a d, something like a d, let's just say f of I for now, where f is some function, I squared, I over 2, something. We get some kind of function of I showing up over here. In that case, it's this term that we really need to isolate, and we can write it now as a sum. Here I'm going to write it, the sum, I equals, now where do we start? My I, so here I've got my index I, right? This is I. Where did we start? We started at 0, so I equals 0. Where do we end? Now here we need to be careful. It looks like it's k, but actually we stop at the level right before, k minus 1. And what are we summing over? Well, this was the term we're summing over, d. Okay, so this sum. And now this sum, whatever sum when we do the recursion tree technique, we're always going to end up with two terms. And one or the other is going to be bigger, and it depends on the recurrence that we're looking at, which one's going to end up being bigger. So we always need both terms, and we're going to take a look at both terms here. But then what we just need to do is simplify to get our bound. So let's do that together. So the first one here is the C plus, and we can see here the D, we can factor the D out. We get the sum, I equals 0. I'm just leaving it as a k now, k minus 1 times 1, which again, carrying this math out, the C by itself, plus the D looks like times a k. The whole sum becomes a k. So now we need to know, well, what is k? And that's where we get here. We had our n minus k is going to be less than or equal to 1. And specifically here, we're going to be concerned with actually equal to 1. When is it going to be actually equal to 1? The first time we get this is when it's going to be equal to 1. So a little bit of math here, not too much. We want to know what value of k is. So the first thing I'm going to do is I'm going to move my k to the other side. I'm going to get k, and I'm going to move the 1 back over here. So we'll get n minus 1 is equal to k. And that's probably makes sense, because that's telling us how many steps do we need to go down before we get to size 1. Well, we need to do n minus 1 steps down. So it looks like our k here is n minus 1. So we can complete our math here, c plus d times n, and then I'll do a minus d here for the minus 1, multiplying my d through. And then maybe just to gather it in a more complete way, we have d times n, that's the correct one, or that's our dominant term, plus, and then maybe I'll do a c minus d is the constant that we have at the bottom there. All of that, we should hopefully come up with a good guess here. That looks like this is a linear time function. Okay, so here what we've done is we've explored the recursion tree technique, where we started with a tree and we filled out this table as we went. And really what we were trying to do was isolate a pattern on the ith level here, and this term here we turned out to be a d. From that we decided let's sum up this column here. This column will be the total cost of the whole recursive algorithm, and then a little bit of effort to simplify that sum brought us to the conclusion that this is probably a linear time or an order n algorithm. If we want to demonstrate this, now we've come up with a guess here, and if we've been actually really precise with our math and we haven't made any errors, then we might be confident that this guess is true. But if not, then the next technique is, or the next step is to use induction to prove that this is going to be true. Okay, let's explore that technique again using our second recurrence relation here. Now in this case, I've swapped out for our binary search case, our binary search recurrence relation. And so now I have the floor of n over 2 here. Let's see how that changes things in our calculation. So again, we're going to start on the first level, and for convenience I'm going to start with level equals 0. The size on, or the number on each level is still 1. This is going to not change. The structure of our tree is still the same here. The size on our first level will be n, and the cost on this level again will be d. Copying the cost here. Sometimes this will be a function of n, but in this case it's not, so we just get a constant. Next level down, we're going to have a 1 here. The number on this level is still 1. The size, and we want to be careful here, is the floor of n over 2. So in our last example where we had n minus 1, we now have the floor of n over 2. But the cost on each level is the same. We still have our d. Okay, let's continue. Now we want to make sure we get our pattern correct. We're on level 2. We still have 1. And now let's maybe just investigate this here. What we technically have is the floor of n over 2 all over 2. And that's messy. I don't like that. How can I fix this? Well, it turns out, luckily, this is equal to the floor of n over 4. And if you want, you could maybe take a moment to try and prove that to yourself. A little bit of discrete math, and you should be able to do that. So we get here the floor of n over 4. Again, the cost on this level is d. We probably see here that now if I go down to my level I, or my more general level, we'll still have 1 here. It looks like now we have n over 2 to the power of I. Again, the cost here still being d. On to the final level then, k. Again, remember the defining feature of level k is that its size was supposed to be less than or equal to 1. That was the terminating criteria. So I'm going to write that again. That's going to be n over 2 to the k, the floor of, must be less than or equal to 1. Now remember, we used this to figure out what k was in the last example. So again, I might highlight that. This is what we need to use in the example. There's still 1 on this level, and like the last example, we're now in the terminating case, so we're at c instead of d. But again, it looks like it's going to be a sum of this column here that we need to use to express the final runtime. So we're going to get, again, our c as our single term, plus, now try and build the sum with me again. We're going to start at I equals, here I've got my I, my index. Where did I start? I started at 0. Okay. Where did I go to? Remember, down to level k, but not including that level, so it must be k minus 1. And the term I'm summing over is always listed here on row I in the column under our cost. In this case, it's not dependent on I, it's just D. Oh, well, this was actually the exact same expression we just had. The main important thing is our k is going to be different here. So maybe I'll just skip over the steps that we did there and jump to our conclusion was that this was d times k, c times d times, or c plus d times k. So we now need to know what k is. Well, again, in this case, and I'm going to just blur my eyes at the floor for a second, let's imagine a case where we had n to the 2 to the k. Let's find one where it was equal to 1. Well, what we're saying here is n must be equal to 2 to the k. Hopefully we see that by taking log of both sides, we get k is equal to log n. So this is going to be c plus d log n. Again, if our goal in this technique is to come up with a good guess for our runtime, our good guess here should be log n. And that matches what we know about the binary search algorithm, is that indeed it has a log n runtime. If we don't believe the guess, or we don't trust it, or maybe we need to convince someone, again, we can use induction to prove this, and in a future video I will go ahead and do that. All right, for our final example, I wanted to take a look at the recursive, the recurrence relation where we had 2 recursive calls on each level, each one being about half the size. And remember, we still are only doing a constant amount of work as we for each recursive call. Actually, we're going to need an extra column here. We're going to need an extra column called total, because this column here is now going to be the cost per node. We're noticing that now we have multiple nodes on each level. This number column is going to start to become relevant. Let's just start out again filling in the elements for our first level. We have, I'm going to start on level 0 again to make our math work out properly. We're going to have 1 node on this level, again size n on our initial level. The cost per node, looks like we got a D here. The total cost now, this is the cost per node, so we need to multiply by the number of nodes. It looks like we get D. Okay, good. So now let's go to the next level down. This is level 1. How many on this level? Now this is the change. We've got 2 on this level. The size on this level, let's be careful. We saw this in our last example. Floor of n over 2. And the cost per node is still D, so that hasn't changed. But now the total here is 2D. Okay, so now the pattern is changing. Remember, this was all D's all the way down last time, matching this column. So let's continue and make sure we get our pattern correct here. So in the next level down, the number is, we can see here, 4. We did this math last time. It's going to be n over 4. We get D. It looks like we now get 4D for our total in this column here. All right, often I'll go one step further just to make sure I've got my pattern. I think I've got my pattern right, but now I want to start writing it in the way that I think it's right. The next level down I have 8, but I'm going to write that as 2 to the 3rd. And keeping in mind here the same thing here, n over 2 to the 3rd. That number showed up here and here. So we get D, and it looks like 2 to the 3rd D. So that now when I get down to my level I can say, on this level there will be 2 to the I. And the size on this level is n over 2 to the I. I can see the pattern very clearly. D and 2 to the I times D. Okay, now remember the last level, K, that's the special level. That's where we end up in the terminating condition. So the cost on this level is C. And also again on this level, maybe I'll be careful, n over 2 to the K must be less than or equal to 1. Remember, I'm going to use that to figure out what k is in a bit. How many on this level? Well, this pattern still continues, so there must be 2 to the k on this level. So again, we get something different here. We get 2 to the k times c as the total on this level. So if we want to put this all together now and come up with you know, a mathematical function to express this, we're going to, again, remember there's 2 terms. The first term, remember, we're going to sum up this column. Okay, the first term is just the grabbing the bottom term by itself. So I'm going to write 2 to the k times c plus, and then my second term should always be a sum, and I start I equals 0, remember 0, my column here is telling me what I'm doing, my I equals 0, up to what? Well, again, tells me here, k minus 1, up to this level but not including it, so k minus 1. And now it's critical that we follow the technique properly. This term with the I in it, again, on row I, in this column that we're trying to sum up, it tells us the term we need to put in our sum right here. So we need to copy that over. It's 2 to the I times d. And this is where we want to continue with our analysis. And there's really 2 steps we can do here. We can figure out what k is right away and plug it in, or leave it until we need it at the end. I usually leave it to the end just because I anticipate it's going to make things a little bit uglier. I might rewrite my first term here as c times 2 to the k. c is the constant, so I'm going to put it out front. Plus, now here, my d does not depend on my I, but the 2 to the I does. So I can bring the d out front, and I get myself the sum I equals 0 to k minus 1 of 2 to the I. Okay. Now, this is a sum that we want to know the solution to. I think we may have encountered this in an earlier video, but if not, let's take a quick look at this one here. The sum here, we have I equals 0 to k minus 1 of 2 to the I. Now this is called a geometric series, and in fact it corresponds to a binary number. Let's say this binary number here, keeping in mind here that if we were doing the sum here, this is 2 to the 0, 2 to the 1, and so on. If we added these up, let's say this is k minus 1. If we add all those up, that will tell us the value of this binary number. So when we ask ourselves, what is this sum, we're really saying, what is this binary number equal to? And I don't know what it's equal to unless I do this. If I add 1 to it, I'll notice I get, again, dot, 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 1. I'll actually get 1 extra 0 here. There will be k minus 1 zeros. So my number is 1 larger with the carry, 1 bit larger. And that number, I do know what it is. It's the next power of 2 up, 2 to the k. But to get there, I had to add 1. So this sum that I'm looking at must be 2 to the k minus 1. So if I know that, maybe I knew this already, I can now simplify or solve my problem. I can get my c times 2 to the k plus, now my d here, this whole sum must be equal to the next power up, 2 to the k minus 1, which again, we can maybe write more conveniently. We get c times 2 to the k still there, plus what? D times 2 to the k minus d. So we really need to know what this 2 to the k term is. And remember, we solved this one in just our previous example. In this case, our k was equal to log n. So rewriting this, we get c times 2 to the log n plus d times 2 to the log n minus d. Well, 2 to the log n, this is log base 2, remember, so we cancel those 2 out. We actually just get c times n plus d times n minus d. Again, all of this is sufficient to make a good guess here. Looks like our guess for the runtime for this algorithm should be linear as well, order n. Now, maybe it's worthwhile to reflect that this analysis is analysis of 3 different algorithms. Our log n algorithm was the binary search algorithm. The other 2 algorithms were recursive search algorithms of unsorted lists. One was a more straightforward sequential search from the beginning to the end, and the other one split it in 2, very similar to a binary search, and that was this algorithm we were looking at here, or the analysis we completed right here. And in this analysis, we determined that that algorithm was also linear, or a good guess for that would also be linear, meaning that we haven't, by splitting the list in 2, since we still have to search the left and the right, we still have to search all the elements in the worst case, meaning we've run into a case here where we still have a linear time algorithm despite having a different algorithm, one we maybe thought was more cunning. Turns out it's not more cunning in the sense that it does not get us a better runtime. Okay, so the topic of this video was to focus on the recursion tree technique, which I've now done 3 examples of. I will probably do a few more examples of this in future videos, but the next couple videos that I want to take a look at, I want to look at the follow-up to using the recursion tree technique to come up with a good guess for our recurrence is now to use mathematical induction to prove that this recurrence T of n, to show that T of n is in theta of n. To prove this, we'll use induction. That's going to be the topic of my next couple videos. So thanks for watching, and we'll see you in the next video.